Okay, hello everyone. This is time series analysis MMA 702. This is lecture 3. This is a bit more illustrative than a full-time session. This is intended just in case you finish. I mean, you look at the length of this video and it's a bit shorter. This was originally intended as a 1 hour lecture with 3 hours of artwork. Not hardware, right? Hardware, like in the lab. This is probably one of the heaviest lectures, practically speaking. Before we begin, I highly suggest that everything I mark as an example, even the things I already mentioned, you at least try and go and check yourselves, because that will make this one so much more significant, actually. So there we go. Now it's time to speak about time series. Starting with seasonal time series. Seasonal time series are times that have periodic patterns. They are useful in a lot of fields, predicting quarterly earnings, pricing weather-related derivatives. Like, for example, in the same season, you can expect similar weather in the same place, given some data. Analysis of transactions data, high frequency data, for example, U-shaped patterns in intraday trend intensity, volatility of assets, some actually flowing in a periodical fashion. Here we have some pretty nice examples. For the first one, I would like you to compute the sample autocorrelation function of the series and the difference data. And for year two, I think we have the graphs right here. This is the template for the monthly U.S. housing starts. This is the template for quarterly earnings of Johnson & Johnson. You can see that as long as it keeps ramping up, there are always like this kind of hops. This is a really nice example of periodicity. And well, for the logarithmic earnings, we have pretty much the same. This small jumps, this periodic character, with the quarterly earnings per share of I don't know what KO means, but it's probably a Coca-Cola company. We see again that the quarterly earnings go up and down and up and down. It looks pretty regular, actually. So yeah, these are still really good examples of periodicity. Now, regarding multiplicative models, we're going to consider the housing start series. We're going to let YT be the monthly data. Again, Y is from year. We denote 1959 as year zero, so we can write the time as year plus month, for example. Our first point of data would be Y1, Y01. If we go to the next year, Y14 would be Y1 would be the equivalent of Y12, like February of the. I think that's an errata. Yeah, that was definitely an errata. It's yeah. No, no, wait. No, it's not. I was thinking on the possibility that we use month and year together, but instead what we're going to do is to sum them, just so we can plot the data together as one series. This is what you're doing is make a table transition into a row, or vice versa, and that explains the 14. Now, the multiplicative model is based on the following. The column dependence is lag dependence. We will call that regular dependence. The row dependence is year-to-year dependence because each row represents 1 year. We will call that seasonal dependence. And well, multiplicative model has an interesting property. It says that these two dependencies are orthogonal to each other. So now I'm going to give some words about the airline model for quarterly series. It has two nice forms. The first one, in which you can see it's a sort of pharma model. I mean, it's missing t minus 2 and t minus 3, but it looks like what we are considering is the quarter we're in, the previous quarter, the quarter we were in last year, and the previous quarter 2 hours, but 1 year before. So that's what we are playing with. This is the corresponding difference series, W sub t. This is called regular and seasonal. These were called regular and seasonal difference series. Autocorrelation function of W sub t has a really nice symmetric structure, which is this here. Rho s minus 1 equals rho s plus 1 equals rho 1 times rho sub s. This is fantastic. Also, if L is much larger, like in much larger, then s plus 1, the autocorrelation functions tend to zero very quickly. This model has some nice advantage. It's widely applicable to many seasonal time series. Not many. Well, actually, yes, many. A lot of seasonal time series. Like this is most likely the 101 of seasonal time series. Multiplicative model means that regular seasonal dependencies are roughly orthogonal to each other, as we have just said. The forecasts exhibit the same pattern as the observed series, which is pretty interesting because it talks about some regularity even in the forecast. Of course, since these look a lot like an ARMA model, exponential smoothing looks on point. So this is the forecast plot for the quarterly earnings of Johnson & Johnson. Here I'm trying to forecast the 1981 and 1982. Which looks pretty reasonable, right? Now, for month, if we use monthly data, we're going to use the B notation because it's super practical. Instead of considering that the year has 4 periods, 4 quarters, we're going to consider months from which we have 12. So our model becomes like this. Now, what's the pattern of ACF? This one's for you. You will find it in the textbook. Now we have been talking about the data. It's always so interesting to talk about the time series errors, and some regression models we can apply to this series of errors. The motivation is mainly that the serial correlations have generally a big impact in regression, but that impact is often overlooked. It can introduce biases in estimates, bias in standard errors, and so when we test the t ratios we have, they might look reasonable but might be unrealistic. Like they might not be what the data are actually telling us, and the reason is because serial correlations are playing a role here. In order to get that, to test serial correlation between those idiots, we'll use QStat instead of DW, which is less, what's the word? It's a bit less, less rigorous. QStat is a bit more complicated, but it works better. Joint estimation of all parameters is always preferred. It avoids the problem of spurious regression. And for a proper analysis, we should see the illustration below, this one. Now, related issue, why don't we use correlation coefficient R squared in this course? Because it can be misleading. The correlation coefficients we have defined here based on the autocorrelation functions are actually offer a better insight into the relationship between variables. Now, in order to parameterize these kind of models, R uses a model in this form. When there is this transformation, considering that we can put an explanatory variable there. This is the proper way to handle a regression model with time series errors, because W sub t minus 1 is not subject to the effect of x sub t minus 1. Like those as an explanatory variable, they're independent. Like it's actually this x sub t, so you have an isemage of it is the x on the graphs, like x, y, and y are variables, and x is the other axis. So there's no dependence on that, and thus w sub t minus 1 it's not subject to any effect from this variable. However, let's not mix it with this one, because in this one yt minus 1 contains the effect of x sub t minus 1. The meaning of this: autocorrelation functions go to 0 very slowly. For example, we have autocorrelation functions of square root of absolute log returns. They are very small, but they don't want to go to 0. Like they kind of stay there. Like the decay is super slow. So now this means long memory. And when we talk about long memory processes, what we mean actually is that autocorrelation functions don't converge rapidly to 0. Now, how could we model this? Well, we're going to use what is called fractional difference, and is picking up this r sub t. Sorry, I was pointing with a pen. And instead of using an entire number here, we're going to use somewhere between minus 1/2 and 1/2. Theoretically, this is a canon. Like, this is incredibly powerful. This is very important. In practice, it's not as relevant, so we'll probably overlook. However, in R, we have the package rugards that we could use to estimate these fractionally integrated ARMA models. There is another way. It's yet to be determined how important they are, but it doesn't mean we can't work with it already. So we can use package rugards for this. This package can also be used for GARCH modeling, and that's something we will be seeing in lectures 4 and 5, and it's extremely important. It's very important. It's one of the fundamentals of this course. So, for a quick recap of this last chapter, which includes lectures 2 and 3, sample autocorrelation functions give us MA order. Sample partial autocorrelation functions give us AR order. Some packages have an automatic procedure to select a simple model for conditional mean of a financial time series. For example, R uses command AR for R models to embed a model over that. Before forecasting, we must check that the model is properly fitted. Call this residual autocorrelation functions, call it heteroscedasticity. Next, regarding interpretation of model, if we're working with AR1 with one coefficient phi sub 1, the speed of a mean reversion is measured by half-life, which is calculated in this way. For an MAQ model, forecast revert to the mean in Q place 1 steps, and that's fixed. So half-life is really not important. Now, what is important is to make proper use of regression models when working with time series errors. A good example of this would be regression with AR1 residuals. And it's just a procedure like Cochrane, ORCAD, or even Jumbox is good for a joint estimation. Sorry, delete that one sentence. So we have seen the basic properties of random walk model, regular random walks with drift, and finally the airline model. Well, I think you can throw a wild guess, and obviously guess why it's called airline model. It's very simple in structure, but it's pretty interesting. It's easy to work with. Before lecture 4, I will try to bring you an example of the airline model so you can see better. And this was basically it for lecture 3. I will re-upload lecture 2 because I had an issue with the recorded program, and it only recorded the left half of the screen. So it's a little bit awkward to watch, really. Yeah, that was basically it for this week. Remember to send me participants for each group and together with which topic you will be choosing. There will be 3 topics, topics 1 through and 3. You are free to choose whatever you want, but between all the groups we will do, I want at least one group to cover each of them. And also the first part of project 1 examination will be up tomorrow in the morning. So please stay tuned for that. Okay, thank you for listening. Have a nice week. Stay healthy, stay safe, and study hard.